Standard light sources emit photons randomly in all directions with varying phases. This randomness limits their utility for precision tasks. In contrast, lasers produce a stream where every photon moves in lockstep. Understanding this shift from chaos to order requires examining the quantum mechanical processes that govern electron transitions and energy states within specific materials. After that first surprise, we can slow down and trace the mechanism behind laser fundamentals, the physics of coherent light from the first physical step, so the effect stops feeling mysterious and starts feeling engineered. To understand laser physics, we must first establish the baseline behavior of standard light sources through random electron relaxation events. In a typical thermal source like an incandescent filament, electrons occupy excited energy states due to heat input from electrical current. These electrons undergo spontaneous emission when they randomly drop back to lower energy levels without external influence or coordination. Each transition event occurs independently according to quantum mechanical probability distributions that govern electron transitions between discrete states. The resulting photons are emitted in random directions with no fixed phase relationship, creating the incoherent light we observe from everyday bulbs. This contrasts sharply with laser operation, where emission events become synchronized through external triggering mechanisms rather than remaining stochastic processes. This stochastic foundation sets the stage for understanding how external triggers can override random behavior to produce coherent light through stimulated emission mechanisms. Pause 0.8. To understand how lasers generate coherent light, we must examine the specific quantum mechanical process known as stimulated emission. This phenomenon occurs when an incoming photon interacts with an electron already residing in a higher energy state within an atom or molecule. The electric field of this incident photon perturbs the excited electron, inducing it to drop back down to its lower ground state. As the electron transitions downward, it releases a second photon that is identical in frequency, phase, polarization, and direction to the incoming trigger photon. This process strictly adheres to conservation laws where the energy difference between the two states equals the photon energy, ensuring momentum remains balanced throughout the interaction. Unlike spontaneous emission, which occurs randomly without external influence, stimulated emission creates a cascade effect where one photon becomes two perfectly synchronized copies. We can visualize this as an incoming wave prompting an excited system to emit a clone that travels in perfect lockstep with the original signal. This precise duplication mechanism forms the fundamental basis for light amplification within laser media before we consider how to achieve net gain. Pause 0.8. To understand laser operation, we must first define population inversion. In thermal equilibrium, most electrons occupy lower energy states according to Boltzmann's statistics. This distribution prevents net light amplification because absorption exceeds stimulated emission. Population inversion requires more electrons in an excited state than a ground state. Consider two energy levels where the upper level holds more particles than the lower one. This condition creates a non-equilibrium state essential for coherent photon generation. Achieving this distribution demands external energy input to overcome natural thermal tendencies. Pause 0.8. Achieving population inversion requires an external energy source to actively drive electrons into excited states against their natural tendency to relax. This process is known as optical pumping, where photons from a flash lamp or laser diode are absorbed by the gain medium atoms. For instance, ruby lasers utilize high-intensity flash lamps that emit broad-spectrum light to excite chromium ions within the crystal lattice. Alternatively, gas lasers like helium-neon systems employ electrical discharge tubes, where free electrons collide with atoms to transfer kinetic energy directly. These distinct mechanisms illustrate how thermodynamic work must be performed continuously to maintain the inverted state against spontaneous emission losses. The choice of pumping method fundamentally constrains which materials can function effectively as gain media in practical laser designs. Understanding these input methods reveals why certain materials are better suited for specific applications based on their energy level structures. Pause 0.8 The choice of gain medium fundamentally dictates both the operational wavelength and amplification efficiency of any laser system. This selection relies on specific electronic band structures that define available energy transitions for photon emission. For instance, solid-state crystals like neodymium-doped YAG utilize discrete atomic levels to produce stable infrared light at 1064 nanometers. In contrast, gas mixtures, such as helium-neon, rely on collisional excitation between atoms to achieve population inversion in a continuous flow. Semiconductor materials differ further by utilizing band-to-band transitions within a crystal lattice structure for compact device integration. Each material class presents unique trade-offs regarding thermal conductivity, transition cross-sections, and required pump power densities. Understanding these intrinsic properties allows engineers to match the medium precisely with the intended application requirements. With the gain medium selected, we must now examine how optical feedback structures sustain coherent oscillation within the system. Pause 0.8 The optical cavity consists of two precisely aligned mirrors that trap photons within the gain medium. These mirrors force light to bounce back and forth repeatedly through the active material. Each pass allows stimulated emission to amplify the existing photon stream significantly. Resonance occurs only when the distance between mirrors matches integer multiples of half wavelengths. This condition creates standing waves, where constructive interference reinforces specific frequencies, while others cancel out. For example, a cavity with 30 cm spacing will selectively sustain light at wavelengths that fit perfectly within this boundary. Without these resonant conditions, photons would escape before achieving sufficient amplification for laser output. Pause 0.8 The core mechanism driving laser operation is a chain reaction of stimulated emission events that exponentially multiplies photon count. When an initial photon passes through the gain medium, it triggers excited atoms to release identical photons in phase and direction. Each new photon can then stimulate further emissions, creating a multiplicative cascade within the optical cavity. This process continues until the rate of photon production balances with losses from mirror transmission and absorption. For example, starting with one photon, repeated cycles through the gain medium can generate millions of coherent photons in microseconds. The exponential growth depends on the gain coefficient exceeding total cavity losses to sustain net amplification. Pause 0.8 To understand temporal coherence, we must examine how the phase of a light wave maintains a predictable relationship over time. Unlike ordinary light sources where phases shift randomly, laser emission preserves a fixed phase difference between successive cycles. This consistency arises because stimulated emission forces new photons to match the frequency and timing of existing ones within the cavity. Consider a waveform overlay where multiple cycles align perfectly. Peaks coincide with peaks while troughs remain synchronized across extended durations. Such alignment indicates that the wave maintains its shape without random phase jumps, which defines temporal coherence in physical terms. The narrower the spectral width of emitted light, the longer this coherent duration extends due to Fourier transform constraints on frequency and time domains. This mechanism ensures monochromatic output, because only frequencies within a tight band can sustain stable interference patterns over measurable intervals. Pause 0.8 To understand why lasers produce such tight beams, we must examine the spatial coherence of their wavefronts. Unlike a light bulb, where photons travel in random directions with varying phases, laser light maintains a uniform phase relationship across its cross-section. This means that at any given moment, every point on the beam's surface oscillates in perfect synchrony. Imagine standing in front of a flashlight versus a laser pointer. The flashlight spreads rapidly because its wavefronts are curved and misaligned. In contrast, the laser maintains nearly planar wavefronts that propagate forward without significant spreading over distance. This property is governed by diffraction limits, which dictate how much a beam can naturally diverge based on its initial width. A Gaussian beam profile describes this intensity distribution, where energy concentrates along the central axis and tapers smoothly toward the edges. The result is a highly collimated output capable of maintaining focus over long ranges compared to conventional sources. Pause 0.8. The laser cavity requires 2 mirrors to sustain oscillation, but one must be partially transparent to release the usable beam. This component is called the output coupler, and its transmission coefficient determines how much light escapes versus remains inside for amplification. If the mirror were fully reflective, no energy would exit the system despite internal gain processes occurring continuously. Conversely, excessive transparency would prevent sufficient photon buildup needed to maintain population inversion thresholds. Consider a typical helium neon laser, where the output coupler transmits approximately 4% of incident photons per pass. This specific value balances extraction efficiency against cavity losses to achieve maximum steady-state power output under given conditions. The resulting external beam path emerges as a coherent wavefront carrying energy away from the resonator structure for practical use. This controlled extraction enables applications requiring directional precision, such as surgical instruments or industrial cutting systems. Pause 0.8. We have traced the path from random electron relaxation to controlled photon generation. The transition relies on specific energy state manipulations and resonant feedback loops.